The bigger an explosion, the more obvious the inadequacy of our standard instruments of measure. Here, the measuring stick, the ticking clock, are ridiculously out of place. Explosions do not submit to subjective rulers, like meters, yards, or cubits. Explosions don't care about what some king long ago decreed to be the standard, the ruler of the ruler. Explosions are quite insensitive to the length of our feet or to the number of our fingers. In fact, nature couldn't care less about our subjective units, international or imperial, and has little respect for the 10 digits that we've been using as our arbitrary base for reckoning. In this 7th episode, we will show that explosions provide a great example of the inherent indifference of nature on our arbitrary subjective standards to measure and to count. We will show that any explosion not only provides its own objective units, but also its own base for counting. After spending the last few episodes freeing ourselves from subjective units, it is now time to do physics beyond base 10. After these grand claims, let's go back to something we know quite well by now. This logarithmic plot represents the radius of the main front of the Trinity explosion, given in meters with time in seconds. In the first picture, taken 0.1 milliseconds after detonation, the explosion has already grown into a ball of fire with a radius around 10 meters. 3 milliseconds later, the radius of the explosion is around 60 meters. After 15 milliseconds, it is over 100 meters. After 100 milliseconds, the shock front has separated, leaving the fireball behind and becoming increasingly transparent. After a few seconds, the shock front is almost 3 kilometers away, and its position cannot be measured optically anymore, and the data points rely on pressure measurements, the subject of the next video. We've seen in the previous episodes that these kinematics of the explosion can be understood by invoking a domain of 4 constant mechanical quantities: the energy E of the explosion, the ejected mass m, and the density and stress of the ambient medium, air for Trinity. These 4 mechanical quantities take turn in governing the dynamics over their respective neighborhood of influence. From the set of 4 mechanical players, there are 4 trios associated with spatial space-time points, remarkable events. For instance, in the top right corner is the Hopkinson-Kranz point, with coordinates given by the interplay of energy, density, and stress, one of the trios of the domain. Similarly, each one of the other points is associated with one of the remaining possible trios. A line between 2 points is associated with the 2 mechanical quantities in common between these points. This particular line was the first we encountered. It is Taylor's regime, while the kinematics result from the interplay of the explosion energy E and the ambient density ρ. With this pair, the energy is necessarily the impelling factor, and the density is the impeding factor. The initial regime involves energy and mass. The shock's final trajectory follows the propagation of sound. These 3 regimes are enough to describe most of the dynamics of the main front of the explosion. But we've also seen that the interplay of energy and the ambient stress gives the final blast radius, which we will discuss more in the next episode. There is also the size, where the mass of swept-up ambient air is equal to the ejected mass, and the mysterious shrinking regime, on which we'll come back another time. It is here, but since we don't need it, we'll forget about it for now. The mechanical constants of the domain imply that the kinematics of the explosion must follow the template drawn in red, with axes and intersections differing quite clearly from the arbitrary frame we've been using to represent the data. This conventional straitjacket has been boxing us in long enough, and we've actually seen already how to free ourselves from it. First, we must adjust the units to align with one of the spatial points of the domain. For instance, we can choose the point on the bottom left to be our logarithmic origin, so its coordinates provide new units of length and time, more objective than the meter and second. If this system of units is compared with the arbitrary one we started with, we know that the coordinates of all spatial points of the domain can be expressed from rational powers of n, the index of the domain. The next step is to officialize the deposition of base 10 and to realize that the index provides a more objective radix, that is, a more objective base. Let's compare more closely the two types of scales, subjective and objective. Take a look at the top scale, 1, n to the power 1 over 6, 1/3, 1/2, 2/3, and 5 over 6. The fractions are given in irreducible form, which obscures the linear progression of the exponents, with n to the power 1 over 6 raised to the power 0, 1, 2, 3, 4, 5. We know that the index is really defined modulo, an overall power. So let's introduce a number r equals to n to the power 1 over 6. Using this definition, the objective scale can be written in a way that makes the comparison with the subjective scale more apparent. The number r, that is a reduced form of the index, is the radix of a different numbering system beyond base 10. R is a base much better suited to the description of explosions, much less arbitrary than the base 10 we've been using, pushed by the unfounded assumption that this sacred 10 was out of the reach of the mechanics at play here. The grid imposed by the arbitrary choice of units and by base 10 is obviously misplaced, unable to capture the important events of the explosion. In contrast, the grid associated with the objective units and a suitable radix is neatly aligned with the kinematics. Of course, we know that if we move around the origin to one of the other special events, the index and so the radix, the base r, remains the appropriate choice. So we have it. Not only does the domain of 4 mechanical quantities give us the 6 regimes, the 4 systems of objective units, but also a single index which we can use to build a radix, a new base to count, to replace the 10 digits of our fingers. And this last step, the overthrow of base 10, is exactly what we have been waiting for to finally overlap explosions occurring on different scales. We now have a fully objective representation of the domain. Take for instance the Hopkinson-Krentz units. You may recall this plot from the last episode, collecting explosions with very different values of index or initial Mach number. With this choice of units, of course, the portions of each explosion abiding to Taylor's regime or to delayed dynamics following the speed of sound, these portions overlap neatly. But the initial regimes produce a splay of different curves, one for each value of the index. And if we were to move the origin to one of the other 3 spatial points, we would face the same dilemma. Part of the dynamics would not overlap. In the last episodes we used the metaphor of the blanket too small to illustrate this situation. It's cold, but your blanket is too small. You can choose to cover your feet, the early crossover, but your head gets cold, the light dynamics. Or you can cover your head, but your feet get cold. We know now what was missing. We know that the size of the blanket is here arbitrarily set by the base 10 we use on the axis, whereas we should really tailor a base for each explosion, a base given by the index. Let's look at Trinity again, in the Hopkinson-Krentz units. If we now plot a different explosion in the same units, like the laser-induced explosion by Grun and coworkers, then only the values on the axis on the left and on the bottom have changed. The measurements of the explosion differ in conventional subjective units of meters and seconds in base 10, but they are the same in objective units when we use the index to select the appropriate radix. The values on the right and at the top have not changed. The values in conventional units of the Hopkinson-Krentz units L and tau differ from one explosion to another, but they are constructed in the same manner from the mechanical parameters. Similarly, the value of the base r is not the same here as for Trinity, but it is constructed in the same way from the mechanical parameters. If we return to our splay of curves with different values of the index, we understand now that by constructing objective units, we have only done half of the work needed to fully appreciate the scale-invariant similarity of all these explosions. We've adjusted the units based on the mechanics, but we are shying away from getting rid of this base 10 we seem subservient to. On this template, where the units and the base are built from the relevant mechanical quantities of the dynamics, we can superimpose all the other explosions in our collection. The atmospheric nuclear tests, the conventional explosions, the laser-induced explosions, and underwater explosions. We started this journey with explosions occurring on all scales, measuring size and time with the conventional units of meters and seconds. From this subjective perspective, it was hard to believe that a tiny laser-induced explosion could have much in common with a terrifying nuclear blast, not to mention supernovae. Yet, we realized that the mechanics were similar, involving an interplay of energy, mass, density, and stress. From this mechanical domain, we identified remarkable events, turning points of the dynamics, depending only on the mechanical constants. These points provided more objective units, like the Hopkinson-Krenz units. In these units, part of the dynamics would overlap. Each curve was associated with a value of the index n, but the numbers themselves on the left and bottom were still given with respect to the conventional base 10 instead of this index n, built solely from the mechanical players. Once unshackled from this rarely shaken tradition, we reach a purely objective representation of explosions. All follow the same path across space and time. Well, almost. This very nice plot is actually missing half of the story. All explosions here are detonations, with an index n greater than 1, corresponding to various shades of red. But we know now that explosions are split in two categories: detonations and deflagrations. How can we represent deflagrations on a similar objective plot? For deflagrations, the index is smaller than 1. The distinction can also be done from the radix, the base r, equal to n to the power 1/6. For detonations, that is for r greater than 1, then r to the power -3 is smaller than r to the power -2, which is smaller than r to the power -1, and so on. So sizes get bigger when moving up on the plot, and time flows from left to right. The converse is true for deflagrations. Higher powers of r are smaller. To appreciate how the spacetime plot of the domain changes when going from detonations to deflagrations, let's consider this representation with base 10 in the Hopkinson-Krenz units. The three gray lines are the three trivial regimes in these units. The other lines are the three other regimes of the domain. The color of these lines reflect the value of the index. Here, the index is around 1 million, which corresponds to an initial Mach number of 1000, or a radix around 10. As the index decreases, the extent of the domain shrinks in base 10 until it vanishes for n is equal to 1 and flips upside down when n becomes smaller than 1. For instance here, where n is equal to 0.01, the sound speed is greater than the ejection speed. The inequality between the two speeds is just another equivalent way to distinguish deflagrations and detonations. To which we could add that for deflagrations, the final blast radius is smaller than the length built by equating the swept-up mass and the ejected mass. So all of these statements are equivalent ways to express the distinction between deflagrations and detonations. Then, if we return to our fully objective representation, using the radix constructed from the index, then we have a choice. If we want to maintain axes that are increasing when going up and right, then we need to distinguish two kinds of plots. In both of these plots, time flows from left to right, and sizes increase when moving up in the plots. Let's consider detonations first, since we are more familiar with them. The initial regime is faster than the sound speed. Once the swept-up mass becomes greater than the ejected mass, the main front of the explosion follows Taylor's 2/5 regime. Eventually, the front reaches the Hopkinson-Kranz point, the origin of this system of units. This radius delineates the final blast radius, within which most damage occur. The shock front itself carries on much weakened, practically indistinguishable from a sound wave. These are the main phases in the life of a detonation. For deflagration on the other side, the initial regime is now slower than sound. The bang travels ahead of the ejecta. Before any significant swept-up mass can build up, the front reaches the regime facing energy with the ambient stress. For detonations, we call this length the final blast radius, the extent of the main damages. What would happen to a deflagration at the same point? Part of the debris might carry on, but the damages may be contained in a way similar to detonations. As mentioned in the last episode, we have not done our homework yet on deflagrations, so we won't venture further in our projections. We call on you to make any suggestion on this topic under the hashtag deflagration. This is the first option. For a given explosion, we can compute the value of the index. If this index is greater than 1, then we expect the data to follow the red trends on the right, the template for all detonations, when plotted with a base and units constructed from the mechanical parameters of the domain. If in contrast the index is smaller than 1, we can expect something similar to what is outlined on the left, in blue. This dual representation, with separate plots, is required if we care about the traditional orientation of plots, with coordinates always increasing while going up and right. However, we've also grown accustomed to look at the exponents, and we could be a little unsettled by the fact that the progression of the exponents on the deflagration side goes against the convention of higher being associated with up and right. So we can consider the plot of detonations, where exponents are sorted according to our aesthetic preferences. And we can add the deflagration path, for which time flows from right to left, and size grows from top to bottom. For now, this representation may seem a bit exotic, but we will see in future videos, beyond this series, that this representation can be used to reveal essential properties of the interactions of space, time, and matter, as mediated by the mechanical parameters of the domain. When we compare this schematic with the data from our collection of explosions, we see that the agreement is pretty good. It is true that we should be gathering data on deflagrations to populate this part of the graph, and you can help us with that in the comments. It is also true that some explosions with an index close to 1 seem to deviate quite substantially from the 6 regimes of the domain, in particular next to the spatial points. This is a general feature, which will require more time to understand. Eventually, we will need more than 4 mechanical quantities to capture this behavior. We will start to address this important fact in the general series on mechanics. With this series coming to an end soon, we can let ourselves appreciate how far we've come from Taylor and Trinity to this neat example of physics beyond base 10. Our goal was to show that the mechanics at play shape the path of an explosion, revealing units and a numbering system that are far more objective than the second, the meter, and the 10 digits of our fingers. For contrary to the unreasoned opinion of the ignorant, the choice of a system of numeration is a mere matter of convention, Pascal once said back in the 17th century. While it is certainly true that the conventional base 10 should not hold a privileged position, what we've seen with explosions is that the mechanics at play in a particular situation shape the most appropriate base. Mechanics selects the right convention. The radix is set by the index. This aphorism is the closing word of this series. The next and final episode is more of an appendix, a preview of how mechanics look like when the dynamics are not solely represented as a size over time, but are expressed from combinations of more general kinematic and mechanical variables. This different outlook on mechanics will take many more videos to explore, but explosions still provide a great first introduction.